I've updated the logistic map interactive diagram I made a while ago for my blog, and I thought it would be fun to record a video showing what you can see about the logistic map by playing around with the new interaction. On the left is the same diagram I had from the original blog, so you can drag the red dot to select the initial value for your x value in the logistic map. Here you can click and drag the value for r, which is the growth rate associated with the logistic map. And now you can also drag and change the number of iterations of the logistic map that this is going to calculate. And I think I let it go up to a maximum of 256 right now. In the middle is a diagram that is probably more standard. This is what you see if you look up cobweb diagram on Wikipedia. This includes the parabola showing the mapping from the x value to the next x value that the logistic map specifies. And then it has a line just along the y equals x axis. And so while in the diagram on the left, the way you make updates to your position is you start with an x in the x direction, and then the y value becomes your next x value. Then you move left to intersect with the other parabola, and now you've gone from y being your current value to x being your next value. And so you bounce back and forth with this combination of vertical and horizontal moves, and eventually sometimes you eventually converge to a fixed point. One of the sort of downsides to this is that just reading off like the x positions that you see on the graph doesn't tell you all of the values of your population for the logistic map. You have to kind of bounce back and forth between thinking of your current value as being the x position or the y position. So with the cobweb diagram, what you do is you move vertically to update from your current x position to the y value being the new x position, but then you immediately convert that y value back into an x value by moving horizontally to the line y equals x. So you end up making like twice as many moves. Maybe you can see that if we look down just for two iterations. Here on the left, I go up once and then left once. Here I go up, I go left to convert the y value into an x value, and then I go up again. So you can see a little bit of the difference. This cobweb diagram on the right, you can see just by looking at where horizontally the lines hang out on the picture, what values of the population are being selected for. Though it is a little bit harder, I find it a little bit harder to see convergence to sort of like periodic fixed points. So here, if I make the value of r equal to something like 3, looking at the diagram with the two separate parabolas, you can kind of convince yourself by staring at it that if you bounce back and forth in this particular way and you find yourself at this particular crossing of the two parabolas, that's a period 2 fixed point, and that just kind of reads off very clearly from the diagram. Whereas there's nothing quite so clear in the cobweb diagram in the middle, indicating that this is a fixed point. So it's kind of nice to have the two of them side by side, I think. Maybe one advantage for the cobweb diagram in the middle is that you can clearly see that there's like a periodic behavior. You're going back and forth between x being here and x being there, whereas You have to use a little bit more imagination to realize that because these two parabolas are crossing at a line that is not y equals x, that this involves staying here at this point actually involves bouncing back and forth between two different values for x. And then finally, on the right, I plot a cumulative distribution of all of the different x values that we've visited in applying the logistic map a bunch of times. And so what does that exactly mean? It means that, here, let's just look at it for one iteration. Here I'm starting at this particular value of x here on the left, and after one iteration, x has increased. So if I look at this cumulative distribution, the fact that this plot is 0 to the left of my initial value for x means that 0% of the time do I find myself with a value of x that's less than this value. As soon as I reach my initial value, it jumps up to 50%, which means that 50% of my x values were less than or equal to this particular point along the x graph. And the line stays constant here for a while because I have no new x points. So I still have 50% of my x values are less than or equal to all of these x values. And then finally I get another bump at the second value from iterating my map. If you make the logistic map apply many times, you can see that the cumulative distribution will exhibit these steps at values where the logistic map or your trajectory is hanging out for a long time. So you can see there's a small number of times that we visit x values that are like slightly less than this fixed point value, but they're overwhelmed by the almost 50% of the x values lie within this small range around this part of the period 2 attractor. Again, you'll see there's a small slope here indicating that between this part of the period 2 attractor and this rightmost part of the period 2 attractor, there's a few times that we visit values in between there, mostly while we're spiraling out to hit the steady state. But then again, we find that again almost 50% of the other values, or 50% of the values again, are all within this small distance around the fixed point of the attractor, which is right here. You can use this to see some kind of cool things with more interesting attractors. And here you can actually notice that there are the transition from a unstable to a stable fixed point. So if I go down to a small number of iterations, let's say 16, and I move my initial x value to be very close to hitting this crossing of the y equals x line and my parabola for the logistic map, you can look at the integrated histogram and see that almost all of my values are hanging out around here. So it looks like we've been attracted to a fixed point of the map. And this is a fixed point, but because we didn't exactly hit the fixed point, and because it's an unstable fixed point, as we iterate the map for more and more times, we see in the cumulative distribution that this step at the unstable fixed point eventually becomes overwhelmed by steps at the period 2 stable fixed point. And so it's kind of a neat way to explore kind of the intermediate dynamics of the logistic map. And then of course you can also play around with bigger values of r. You can see more steps appearing in the cumulative distribution, and just the number of steps you have is just the number of it gives you the period of the attractor that you've fallen into. And when you hit, you can see this whole period doubling route to chaos kind of phenomenon, where we start with period 1. Well, I guess we start for r equals 1 where you always decay down to 0. Then we just have a fixed point that's moving up as we make r bigger and bigger. Then eventually we hit our first period doubling around r equals 3. You can see subsequent period doublings, which I think is kind of cool. And then you hit these chaotic regions where you don't have any steps anymore, and it just looks kind of like a chaotic wiggle. Although you can see steps reappear in some of these stable regions in the logistic map. So anyway, hopefully that gives you some ideas for how using an interactive visualization like this might be useful. And I'm looking forward to trying to make more of these going forward.